So for our first new topic in Math 1080, we have something of a gentle introduction to the type of stuff we're going to be doing later on in this class. This is section 6.1, which is about finding area between curves. Now in chapter 5, we kind of led on with the promise of being able to find the areas of more irregular shapes, but the only thing we've done so far is find the area underneath a curve, or the area between the curve and the x-axis. But technically the x-axis is just a function which is identically equal to 0 constantly for all values. So finding the area between two curves should look similar, just maybe in a more generalized fashion involving both functions. So let's start off by asking for the area between sine and cosine. And we'll do that from 0 to pi over 4. That's where they meet. The way this is basically going to end up working is I'm going to find the area underneath cosine of x. And I'm going to subtract the area underneath sine of x. We'll call that one g of x. So if I find all of this area up here, and then I subtract this area down here, then what's left over up here is the area technically below cosine and above sine, so between those two functions. Now in terms of Riemann sums, what this would look like if I chop up my interval from 0 to pi over 4, and this is something we're going to be doing a lot, is a lot of chopping. So if I'm looking at this picture in terms of Riemann sums, then I'm going to be trying to draw rectangles here. I'm trying to find areas of these rectangles. But it's kind of doing two things at once. So if I stick to the right-handed Riemann sums that I'm used to, the area between these two curves, I'll have a Riemann sum. I'll go from I equals 1 up to n. I'll have widths, so we'll call that pi over 4 minus 0 all over n. And then we need the heights of the rectangles. So we're going all the way back to the basic construction of the Riemann sums. The widths of my rectangles, they don't change. It's just going to be b minus a over n. But the heights of the rectangles now, what is the length of this line? Well, the length of this line here is going to be f of x minus g of x. So here I'm going to have f of, see, for right-handed rule, I use 0 plus I times b minus a over n minus g of same thing. And I'll rewrite that because that looks a little bit ambiguous there. I equals 1 up to n of pi over 4n times f of pi times I over 4n minus g of pi times I over 4n. Where here I have the widths, and here I have the heights of each rectangle. And if I were to break this Riemann sum apart, I would notice that this is the same thing as the Riemann sum for f of x minus the Riemann sum for g of x separately. So when approaching these problems in terms of strictly Riemann sums, we typically stick with the more condensed x formulas as opposed to the b and a formulas. So we're not going to be doing this a whole lot quite yet, but in the future we would set up the area between these two functions would be approximately, well, not approximately, but I could say equal to the limit as n goes to infinity, because the integral is equal to the limit of a Riemann sum, of the sum from I equals 1 up to n. I'll keep the b minus a over n, which is pi over 4n, and this is times f of x sub I minus g of x sub I, where the x sub i's are basically just my sample points for my rectangles. So in terms of the bottom line that we get, this is actually going to be an integral, because this is a Riemann sum, and Riemann sums are the same as integrals. So this is equal to the integral from 0 to pi over 4 of f of x minus g of x, or like I said before, this is equal to the integral from 0 to pi over 4 of f of x dx minus the integral from 0 to pi over 4 of g of x dx. So to answer this original question, what's the area between sine and cosine from 0 to pi over 4? Well, f of x was cosine. I'll keep it this way. The integral from 0 to pi over 4 of f of x, which is cosine, minus g of x, which is sine, and when I find this antiderivative, I'll have sine of x minus, actually plus, cosine of x, and that's evaluated from 0 to pi over 4, which comes out to be root 2 over 2 plus root 2 over 2 minus sine of 0 plus cosine of 0. That one is 0, but this one is equal to 1. So it looks like my answer is the square root of 2 minus 1. So in terms of the general formula here, the only thing that's specific about this limit right here is the delta x that I labeled. So we have a definition, I suppose. The area between two curves f of x and g of x with f of x less greater than or equal to g of x on the interval is the limit as n goes to infinity of the sum I equals 1 up to n delta x times f of x sub I minus g of x sub I, or in terms of integrals, it will be the integral from a to b of f of x minus g of x. Now you notice here that I said that f of x was greater than or equal to g of x. And there's a reason for that. And I can use the same function above to illustrate that reason. So let's consider the integral from 0 to pi over 2 of cosine of x minus sine of x. Since there's a difference here, I could expect this to describe the area between the two curves, cosine of x and sine of x, on the interval from 0 to pi over 2. But when I evaluate this integral, I'm going to have sine of x plus cosine of x evaluated from 0 to pi over 2, which is equal to sine of pi over 2 is equal to 1, plus cosine of pi over 2 is 0, minus sine of 0 is 0, plus cosine of 0 is equal to 1. So that's equal to 1 minus 1, which is 0. Fantastic. And there's actually a very good reason for this. if you recall, when I was finding the area below curves, anytime the curve was below the x-axis, I ended up getting negative area. And if we think about the Riemann sum, while looking at this picture, here I had cosine of x on top and sine of x on the bottom. Versus over here, I have sine of x on top and cosine of x on the bottom. So in my Riemann sum or in my integral, I always had f of x minus g of x, or I had cosine of x minus sine of x. But if cosine of x is below sine of x, then those values are going to be negative. So when I'm doing my Riemann sum, the heights of my rectangles on this side are now negative. So my picture is not perfectly to scale, but from 0 to pi over 4 was this left slightly triangular region. But when I go from pi over 4 to pi over 2, I have this right slightly triangular region. On the left of where they cross, right here, my cosine is above my sine, so I want cosine minus sine to get positive heights. But on the right, my cosine is below my sine, so I actually want sine minus cosine to get positive heights. Otherwise, we're going to have areas canceling each other because some of the heights of rectangles will be positive and some of the heights of rectangles will be negative. So I'll say here that the areas cancel out. And we'll generalize our little formula here for the area between two curves. I'll add the word total here. So if I want the total area between two curves instead of just some blind number, is I'll have the integral of the absolute value of the difference. So I'm going to make sure that the heights of my rectangles is always positive. Because my function values here, those are my y values. And so whatever you're integrating, we'll find, is always, or at least a part of what we're integrating, is always going to represent the height of something. GHT, heights are positive. So that way I don't have to worry about one function being bigger than the other. I just have to be careful when I'm looking for the total area to see if my two functions ever cross anywhere. Because if they cross, that means they're going to switch positions, which means I'm going to switch which one I start off with. So if I wanted to do another example like this, I could ask for, find the area between f of x equal to x squared minus 1 and g of x equal to 1/2 x plus 1. And I want to do this, or not from, but on the interval, -2 to 0. And it's usually helpful to draw these pictures just in case. So from -2 to 0, I'm going to be looking at the left side of the stuff. X squared minus 1 looks something like this. Whoa. And 1/2 x plus 1 will look something like this. So since I'm interested in here from -2 up to 0, I'm going to want the area between the curves which is basically negative 2 to 0, absolute value f of x minus g of x dx. But integrals with absolute values are never a whole lot of fun, so I'm interested in finding out where they're equal to each other. Because I see here that they cross, and on the right-hand side, my line is the function on top. But on my left-hand side, my parabola is the function on top. So I'll find out where they cross. I'll set f of x equal to g of x, which is 1/2 x plus 1 equal to x squared minus 1. And I'll try to solve for the x values where this is true. So this means that 0 is equal to x squared minus 1/2 x minus 2. So I'm not sure how I'll factor this, so I'll go ahead and use the quadratic formula. Never fails. See, I'll have negative b, so 1/2 plus or minus the square root of b squared, that's 1/4, minus 4 times a times c, which is 4 times 1 times negative 2, so that's plus 8, all over 2a, which is, that's just 2. So I have 1/2 plus or minus the square root of 1/4 plus 8. Let's see, 8 would be the same thing as 32 divided by 4, so this is 33 divided by 4, which is just absolutely awful. But I can factor out the 4. I'll have 1/2 times the square root of 33. This is all over 2. Or I could rewrite this as 1/4 plus 1/4 times the square root of 33, or 1/4 minus 1/4 times the square root of 33. Wonderful. I don't know exactly what the square root of 33 is, but I can tell you right off the bat that this thing is going to be negative, and this one is going to be positive. So since my integral is working from negative 2 to 0, I'm definitely going to choose this guy right over here, because this is between negative 2 and negative 1. Or, I don't know if it's between negative 2 and negative 1, but I meant to say negative 2 and 0. So I should split my integral right there. So I'll have the integral from, negative 2 to whatever that is, 1/4 minus 1/4 root 33. Now what function is on top over there? The function on top is the parabola. So I'll have x squared minus 1 minus the quantity 1/2 x plus 1. That's dx. And then I'll add to this the area obtained after where I split it. So this will be from 1/4 minus 1/4 root 33 all the way up to 0. And if I check my picture again, after this intersection point, my line is the function which is on top. So I'll start this with the line. I'll have 1/2 x plus 1 minus the quantity x squared minus 1. Now these are just basic polynomials, and so evaluating this integral is just a simple matter of antiderivative and then plug in the numbers. So I'll write that step, but then leave it alone. So this will be x cubed over 3 minus x minus 1/2 times x squared over 2 minus distributes minus x. That's from negative 2 to 1/4 minus 1/4 root 33 plus, the 1/2 x came first, so this will be 1/2 x squared over 2. I'll add some parentheses just so that we don't mix anything together. Plus x minus x cubed over 3. The minus distributes to have a plus x here. And this one is evaluated from the splitting point all the way up to 0. And I definitely want to split it because I'm going to have some things canceling because they switch which one is on top halfway through. Now it's also entirely possible that I can ask a different brand of problem. And this is something that we're going to encounter a couple of times in this class. So I'll ask this question with a picture. I want to find the area of the region bounded by the curves f of x equal to e to the x, g of x equal to x minus 1 quantity squared, and y equals 5. So what does this look like? Well, on the picture, y equals 5 is up here, not to scale. This one would be e to the x, and this one is x minus 1 quantity squared. And the only region that's bounded by all three of these, my picture's probably not great, is going to be right here in the middle. You have to be kind of super careful with these problems to make sure that there's not too many different regions you can make with these, but we're pretty safe with an exponential. Now how do we do this? Well, according to the picture, I've got a spot where the bottom function changes. Here, the top function is y equals 5, and the bottom function is x squared minus 1. But over here, the top function is y equals 5, and the bottom function is e to the x. So what I would have to do is split up this integral where those two functions intersect to change the functions I'm trying to take the difference of. So, I'm going to have two methods of doing this. So I'm going to call this one A. I can have the integral from something, we'll call it A, and to something, we'll call it B, from A to 0, that's where they cross, of 5 minus e to the x. dx. Plus, I'll have an integral from 0 up to whatever b is of 5 minus x minus 1 quantity squared dx. So I'll go ahead and find out what those intersection points are. A is where e to the A is where x minus 1 quantity squared is equal to 5, which means x minus 1 is equal to plus or minus the square root of 5, or x is equal to 1 plus or minus the square root of 5. Now, according to my picture, I have a parabola, and certainly it's going to intersect twice, but the one I'm interested in is the one on the left here. So I'm going to choose the version with a minus. So I'll say a is equal to 1 minus 1 plus 1. A is equal to 1 minus the square root of 5. And for b, b is where e to the x is equal to 5. And if I solve that for x, Well, my only option is natural log of both sides, and I'll have x is equal to the natural log of 5. So that means that b is equal to the natural log of 5. So if I rewrite these integrals, I'll have the integral from a, 1 minus root 5 up to 0, of 5 minus 1 minus x quantity squared dx. Plus the other half of the region, I'll go from the integral from 0 up to the natural log of 5, and there I had 5 minus e to the x dx. And I can do those too. This first integral, I'd have to multiply that out, but then I would have just a simple polynomial, and I can take the antiderivative of that using the power rule. And the second integral will just be 5x minus e to the x, because e to the x is its own integral. But there's a different way to do this. So if we just scroll back up here, we're going to do some clever math, and clever math means we're going to turn our head sideways and look at it. Integrals we can actually handle along any variable. So I could, in this case, do an integral along the y-axis. If I say an integral dx, that means I'm doing an integral along the x-axis, where I'm chopping up an interval of the x-axis into a bunch of different parts. But if I do an integral with a dy, that means I'm doing an integral along the y-axis, and I'm chopping up some interval on the y-axis into a bunch of parts. So what that means is I'm going to kind of be looking at the inverses of these functions. I'll deal with that in a minute, but instead of having a higher y value going down to a lower y value, I'll have a higher x value going down to a lower x value. And this integral looks a little bit like it might be a little bit easier because my top function doesn't change from y equals 1 here up to y equals 5. And my bottom function doesn't change here from y equals 1 up to y equals 5. So I should be able to express this area as a single integral instead of needing two separate integrals with different bounds. So I'll call this one with respect to y. And what this is this is going to be the integral, I'll call it from c to d, of f, g, we'll call this j and k. J of y minus k of y dy. And so these are going to be the heights of my integrals, or heights of my rectangles, but I'm going to be looking at my picture sideways. So the one that goes first is going to be the one with the higher x value instead of a function of x with a higher y value. So I have an f of x equal to, what did I pick for f? E to the x. Okay, f of x equal to e to the x, which means I have y equal to e to the x. So if I solve that for x, I can get x as a function in terms of y. So natural log of y equals x, if I take natural log of both sides. And this is my, j of y function. My g of x was equal to x minus 1 quantity squared, which means y is equal to x minus 1 quantity squared. But in order to solve for x, I'm going to have to take a square root. But when I take a square root, I have a plus or minus. So similar to when I tried to find the function of a circle, if I tried to solve the equation of a circle for y, I'm going to end up with two choices. I can express the top half of the circle with a square root, or I can express the bottom half of the circle with a square root. And the same thing is going to happen to this function. I'm going to have the top half of the parabola, or in this case, it's going to be the right half if I use the positive, or I'll have the bottom half, or in my original picture, the left half of the parabola. So I'll write this: square root of y equals x minus 1, or the square root of y plus 1 equals x. This is the right half. On the other hand, I can have minus y, square root of y, plus 1 equals x. This is going to be the left half. So back to my picture, I'm concerned with the left half of my original parabola. So right here, I'm going to use this as my k of y, which means I'm going to have an integral from some lower y bound to a higher y bound of j of y, which is natural log of y, minus k of y, which is, in parentheses, let's do 1 minus the square root of y, and this is dy. If I were to take what I've written here and redraw this, I would end up with kind of a flipped sideways version of my original picture if I did everything in terms of functions of x. So back up to the picture. My lower y bound is down here at y equals 1, and my upper y bound is up here at y equals 5. So what I'll do is just rewrite the integral, because my y values, they start at 1 and they end at 5. I'll have the natural log of y minus 1 minus the square root of y dy. And this is where we kind of run into a little bit of trouble for this problem. 1 minus the square root of y dy, I can find the antiderivative of pretty easily. I can just do the power rule. What about the natural log of y? I know the derivative of the natural log is 1 over x, and I know the antiderivative of 1 over x is going to be natural log. But what is the antiderivative of the natural log? It turns out in order to answer that question, we need better integration techniques, because I don't have anything that I can set for u, because I wouldn't have a du for this problem. So next time, we're going to have integration by parts. We'll just say that. So integration by parts, along with u substitutions, those are our standard techniques for solving all kinds of different integrals. And what we're going to do for this class is, instead of following exactly with the book, Chapter 6 is a lot of geometry stuff. We're going to find volumes of revolutions of things and calculate how much work is done by trying to move something. But a lot of times, to solve some of those problems, we're going to need higher integration techniques depending on what kind of functions are involved. So what we're going to do is we're going to start off by gathering up all of our integration techniques, all of the tools we need to solve all the integrals in this class, and then we're going to hit all of the different kinds of applications we can do with integrals, or all the different kinds of things we're going to be able to calculate with integrals, which will hopefully be a lot more fun than what Chapter 7 with integration techniques is going to provide. So when I do integration by parts, we will find out what the antiderivative of the natural log of x is equal to, plus c.